This is the first module of chapter 6. The chapter 6 is devoted to computation of eigenvalues and eigenvectors of a matrix. The computation of eigenvalues and eigenvector is a very important problem of linear algebra. These parameters are used to analyze different problems appear in mathematics, physics, chemistry, different branches of engineering and many other areas. So it is a very important and useful problems, but the computation of eigenvalues and eigenvector is a very difficult problem, particularly for large matrices. In this module, a method is described to compute the characteristic polynomial or characteristic equation of a matrix. By solving the characteristic equation, we obtain all eigenvalues of the given matrix. Now, we define eigenvalues and eigenvector of a matrix in next slide. Let A be a square matrix of order n. If the matrix A satisfies the equation Ax equal to lambda x, that means equation 1, for a column matrix X and for a scalar lambda, the lambda may be a real number or a complex number, then lambda is called an eigenvalue or characteristic value of the matrix A and the vector x is called the corresponding eigenvector. The equation, that means the equation number 1, can be written as A minus lambda I whole into x equal to 0, where 0 is the null vector. The equation determinant of A minus lambda equal to 0 is called the characteristic equation of the matrix A, and this is the very important equation to find the eigenvalues and eigenvector of the matrix A. In explicit form, the characteristic equation or equation 2 can be written as in equation 3. By expanding this determinant, we obtain a polynomial in lambda of degree n, where n is the order of the matrix. That means the characteristic equation of a matrix of order n is nothing but a polynomial in lambda of degree n. The roots of the equation 2, that means the root of the equation characteristic equation 2 or 3 are the eigenvalues of the matrix A. For each eigenvalue lambda I, there exists a column vector xi such that Axi equal to lambda I into xi, then lambda I is the ith eigenvalue of the matrix A and xi is the corresponding eigenvector of the matrix A. The set of all eigenvalues of a matrix A is called the spectrum of the matrix A. It may be noted that if the order of the matrix A is n, then the matrix has exactly n eigenvalues. That means the set of all such eigenvalues is called the spectrum of the matrix A, and the largest in magnitude, the largest eigenvalue is called the spectral radius of the matrix A. Now we state one theorem. That theorem is known as shifting eigenvalues theorem. Suppose lambda be an eigenvalue of the matrix A and capital X be its corresponding eigenvector, and if C is any constant, it may be a real number or it may be a complex number, then lambda minus C is an eigenvalue of the matrix A minus Ci, where C is a scalar, I is the unit matrix of the same order as in A with same eigenvector x. That is, if lambda be an eigenvalue of the matrix A, then lambda minus C is an eigenvalue of the matrix A minus Ci. This property is known as shifting eigenvalues property. Let determinant of A minus lambda I equal to lambda to the power n plus C1 lambda to the power n minus 1 plus C2 lambda to the power n minus 2 up to Cn be the characteristic polynomial of the matrix A. That means the explicit form of the equation 3 is written as in equation 5. Then C1, the first coefficient or the coefficient of lambda to the power n minus 1, which is equal to C1, that means the minus C1 equal to summation over I equal to 1 to n aii, which is equal to the trace of the matrix A. That means the sum of the diagonal elements of A called the trace of the matrix, which is equal to minus C1, C2 equal to the sum of all principal minors of order 2 of the matrix A, minus C3 is the sum of all principal minors of order 3 of the matrix A, and lastly minus 1 to the power n Cn, Cn is the last coefficient which is equal to the determinant of the given matrix A. So, these are the coefficient of the equation 5, minus C1, C2, minus C3, C4 and lastly Cn are obtained by this formula. So, using this method we can determine all the coefficient of the equation 5. But that methods, that means the computation of C1, C2, C3 using the principal minors is a very difficult task. So, Leverrier and Fedov method was developed by Leverrier and later this one is modified by Fedov. This method is used to construct the characteristic polynomial or characteristic equation of any square matrix A. Let det A minus lambda I, which is equal to lambda to the power n plus C1 lambda to the power n minus 1 up to Cn equal to 0 be the characteristic equation of the matrix A of order n or n by n, and let the roots or the eigenvalues of this equation be lambda 1, lambda 2 up to lambda n. This may be equal or this may be unequal. That means the eigenvalues of a matrix may be equal or different, and let Sk be the sum of the kth power of these roots. Then S1 equal to sum of the eigenvalues or sum of the roots of the equation 6, which is equal to the trace of the matrix A. S2 which is equal to the sum of the square of the eigenvalues or sum of the square of the roots of the equation 6, which is equal to trace of the matrix A square, and so on. Lastly, Sn which is equal to sum of n power of the eigenvalues or roots of the equation 6, which is equal to trace of a to the power n. That means equation 7 gives the different values of Sk for k equal to 1 to n. Now, by Newton's formula, which is available on polynomial, theory of polynomial or theory of equation, we have Sk plus C1 Sk minus 1 plus C2 into Sk minus 2 plus dot 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 plus Ck minus 1 into S1, which is equal to minus k Ck, and this relation is true for all k equal to 1 to n. That means this is true for k less than equal to n. So, this is a recurrence relation to calculate the values of C's. So, this recurrence relation among the coefficients of the characteristics equation and all the Sk's. Now, the coefficient of characteristic equation are obtained by substituting k equal to 1, 2 up to n in equation 8 as C1 equal to minus S1. When k equal to 1, then it is easy to observe that C1 is equal to minus S1. When k equal to 2, then C2 equal to minus half into S2 plus C1 S1, where C1 is determined in first equation, and in this way the last coefficient Cn is equal to minus 1 by n Sn plus C1 Sn minus 1 plus C2 into Sn minus 2 plus dot 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 plus Cn minus 1 into S1. All these equations are obtained from equation 8 by substituting the different values of k. Thus, the values of the coefficient C1, C2, Cn of the characteristic equation depend on the trace of the matrices A, A square up to a to the power n, because S1, S2, Sn depends on the trace of the matrices. Therefore, the coefficients C1 to Cn are also depend on the trace of the matrices. Now, the Leverrier-Fedov method generates a sequence of matrices B1, B2 up to Bn shown below. The first matrix B1 which is equal to A, and D1 is a scalar which is equal to the trace of the matrix B1, and then we compute a matrix D1, this one a temporary matrix, D1 equal to B1 minus D1 into I, where I is the unit matrix. Now we calculate the next matrix B2, which is equal to A into D1. D1 is obtained in first row. Then we calculate D2, which is equal to half into trace of the matrix B2, and then we calculate the matrix D2 equal to B2 minus D2 into I. Similarly, we calculate B3 equal to A D2, and D3 is equal to 1 by 3 into trace of the matrix B3, and D3 is defined as B3 minus D3 into I. So in this way, we calculate the n minus 1 matrix B n minus 1 equal to A D n minus 2, and D n minus 1 equal to 1 by n minus 1 into trace of the matrix B n minus 1, and then we calculate D n minus 1 equal to B n minus 1 minus D n minus 1 into I, and lastly we calculate B n equal to D n minus 1 A into D n minus 1, and D n equal to 1 by n trace of the matrix B n, and D n equal to B n minus small d n into I. So in this formula, using this formula, that means using equation 9, we generate a sequence of matrices B1 to Bn. Now the coefficient of the characteristic polynomial are given by C1 equal to minus small d1, C2 equal to minus small d2, and lastly Cn equal to minus small dn. So these are the coefficient of the characteristic equation of the matrix A. It can be verified that Dn, the last matrix Dn, is equal to 0 for any matrix A. Now we consider an example to illustrate the Leverrier-Fedab method to find the characteristic polynomial of the following matrix. This is a 3 by 3 order matrix. So for this matrix, we first calculate the matrix B1, which is equal to A, is the given matrix, and then D1 equal to trace of the matrix B1 is nothing but the sum of the diagonal elements of the matrix B1, which is equal to 3 plus or minus 3 plus 1, which is equal to 1, and B2 equal to A into B1 minus D1I. It may be noted that B1 minus D1I is nothing but the matrix D1, and after multiplication the matrix B2 is a 3 by 3 order matrix whose first row is 10, minus 2, 5, second row is minus 2, 16, minus 1, and third row is 0, 0, 0. Then small d2 equal to half of trace of the matrix B2 equal to half of the sum of the diagonal element, means 10 plus 16 plus 0, which is equal to, after simplification, 13. Then we calculate next matrix B3 equal to A into B2 D2I. Here also B2 minus D2I is nothing but the matrix D2, and after multiplication the matrix B3 is this one. It may be noted that the matrix B3 is a diagonal matrix and all the diagonal elements are minus 13. Now D3 equal to B3 minus D3I as per definition of D3, and after simplification this matrix is a null matrix of order 3 by 3. It is obvious, it is expected that Dn equal to 0, where n is the order of the matrix A. Now D3 equal to 1/3 into trace of the matrix B3, which is equal to minus 13. That means we have calculated all D's, D1, D2 and D3. Therefore, the coefficient of the characteristic polynomial or coefficient of the characteristic equation C1 equal to minus D1, which is equal to minus 1, C2 equal to minus D2 equal to minus 13, C3 equal to minus D3 equal to 13. Therefore, the characteristic equation is lambda to the power 3 minus lambda to the power 2 minus 13 lambda plus 13 equal to 0. It may be noted that the Leverrier-Fedab method can also be used to find the inverse of a matrix. We have mentioned that Dn equal to 0. Therefore, Bn minus Dn into I equal to 0, because capital Dn is nothing but Bn minus Dn into I, or A Dn minus 1 equal to Dn into I, because Bn is equal to A into Dn minus 1, and this equation can be written as Dn minus 1 equal to small dn into A inverse, or we can write A inverse equal to Dn minus 1 by small dn, which is equal to Dn minus 1 divided by minus n. So, using this formula we can compute the inverse of the matrix A. So, Leverrier-Fedeb method is described to construct a characteristic equation of a square matrix A. So, by solving this equation, that means by solving this polynomial equation, we obtain all the eigenvalues of the given matrix A. But the computation of polynomial equation is not an easy problem, but two methods are described in chapter 4 to solve a polynomial equation of any degree n. So, using these methods we can solve this characteristic equation, and by solving this characteristic equation we obtain all eigenvalues of a matrix. But this method, Leverrier-Fedeb method, can also be used to find the eigenvector of a matrix. Now, we describe this method to find all eigenvalues as well as eigenvector of a square matrix A. Now, we describe Leverrier-Fedeb method to find the eigenvectors of a matrix A. Here we assume that the eigenvalues lambda 1, lambda 2 up to lambda n are known, and also the matrices d1, d2 up to dn minus 1 are known. That means, in previously we have already calculated the matrices d1, d2 up to dn minus 1 along with the matrices b1 to bn. So, these matrices are already available, and by solving the characteristic equation we can determine the eigenvalues lambda 1 to lambda n. So, these are known quantities. So, these matrices are available during the construction of characteristic equation, I have already mentioned. Then the ith eigenvector xi can be determined using the following formula, which is given by equation number 11. The ith eigenvector xi equal to lambda I power n minus 1, where lambda I is the ith eigenvalue of the matrix A, into E0. E0 is the unit vector or a particular type of vector, plus lambda I power n minus 2 into E1 plus lambda I power n minus 3 into E2 plus dot 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 plus En minus 1, where E0, E1, E2 up to En minus 1 are the vectors defined as the column vector A0 may be taken as the unit vector, and E1, E2 up to En minus 1 are the column vectors of the matrices D1, D2 up to Dn minus 1 of the same order as A0. So, this is the formula to choose the column vector E1 to En minus 1. Now, we consider an example to illustrate the method to find the eigenvectors of the matrix A equal to, first row is 1, 1, minus 2, second row is minus 1, 2, 1, third row is 0, 1, minus 1. So, for this matrix, the matrix B1 equal to A1, which is nothing but the given matrix given by equation 12, D1 equal to trace of the matrix B1, which is equal to the sum of the diagonal elements, it is nothing but 2, D1 equal to B1 minus D1 into I. After simplification, the matrix D1 is minus 1, 1, minus 2, second row is minus 1, 0, 1, third row is 0, 1, minus 3. This is the D1 matrix. Now, we calculate B2, whose formula is A into D1, and after multiplication, the matrix B2 is minus 2, minus 1, 5, minus 1, 0, 1, and last row is minus 1, minus 1, 4. So, this is the matrix B2, and the matrix and the element D2 equal to half of trace of the matrix B2 is equal to 1, and the matrix D2, which is equal to B2 minus D2I, equal to minus 3, minus 1, 5. Second row is minus 1, minus 1, 1, and third row is minus 1, minus 1, 3. And the next matrix B3 equal to A into D2, and after multiplication the matrix B3 becomes the diagonal matrix whose diagonal elements are minus 2, minus 2 and minus 2. Then D3 equal to 1/3 of trace of B3, and which is equal to minus 2, the sum of the diagonal elements by 3. Therefore, the coefficient of the characteristic equation or characteristic polynomial are C1 equal to minus D1 equal to minus 2, C2 equal to minus D2 equal to minus 1, C3 equal to minus D3 equal to 2. Therefore, the characteristic equation is lambda cube minus 2 into lambda square minus lambda plus 2 equal to 0. And the roots of this equation are minus 1, 1, 2. Therefore, the eigenvalues of the given matrix are lambda 1 equal to 1, lambda 2 equal to 2, lambda 3 equal to minus 1. Let E0 equal to 1, 0, 0. It may be taken as 0, 1, 0, or it may be taken as 0, 0, 1. For this problem, we assume that E0 equal to 1, 0, 0, the first unit vector. Then E1 equal to minus 1, minus 1, 0. This is the first column of the matrix D1. E2 is minus 3, minus 1, minus 1. This is the first matrix, first column of the matrix D2, and that one is mentioned here. The vectors E1 and E2 are the first columns of the matrices D1 and D2. Because E0 is taken as the first eigenvector, so we consider E1 and E2 as the first columns of the matrices D1 and D2. Where D1, the matrix D1 is equal to minus 1, 1, minus 2, minus 1, 0, 1, 0, 1, minus 3. Note that the first column of the matrix D1 is minus 1, minus 1, 0, and the first column of the matrix D2 is minus 3, minus 1, 1. So, that is why we have considered E1 equal to minus 1, minus 1, 0, and E2 is taken as minus 3, minus 1, minus 1. Thus, the ith eigenvector can be computed by the formula. This formula is suggested by Liouville-Fedeb method. The ith eigenvector xi equal to lambda I power 2 into E0 plus lambda I into E1 plus lambda 2. Now, for lambda 1 equal to 1, that means the first eigenvector for the first eigenvalue 1 is equal to x1 equal to 1 to the power 2 into the vector E0, which is equal to 1, 0, 0 plus 1 into minus 1, 1, minus 1, 0. This is the term lambda into E1, and last term is the vector E2, that one is minus 3, minus 1, minus 1. After simplification, this becomes minus 3, minus 2, minus 1. So, this is the first eigenvector, and this is the eigenvector corresponding to the eigenvalue lambda 1 equal to 1. Now, we calculate the second eigenvector corresponding to the eigenvalue lambda 2 equal to 2. X2 equal to 2 to the power 2, where 2 is the second eigenvalue lambda 2 equal to 2 into E0 plus 2 into E1 plus E2. After simplification, it becomes minus 1, minus 3, minus 1. So, this is the second eigenvector or the eigenvector corresponding to the eigenvalue lambda 2 equal to 2. And the third eigenvector corresponding to the eigenvalue lambda 3 equal to minus 1, which is equal to x3 equal to minus 1 to the power 2 into E0 plus minus 1, which is lambda 3 into E1 plus E2. After simplification, it becomes minus 1, 0, minus 1. So, this is the third eigenvector corresponding to the eigenvalue lambda 3 equal to minus 1. Thus, the eigenvectors are minus 3, minus 2, minus 1. Second eigenvector is minus 1, minus 3, minus 1. and third eigenvector is -1, 0, -1. So, these are the three eigenvectors corresponding to the three eigenvalues of the matrix A. In this module, we have defined eigenvalue, eigenvector and characteristic equation of a matrix, and also an efficient method called Leverrier-Fedab method is described to construct a characteristic equation of a matrix. And by solving the characteristic equation, we can obtain all the eigenvalues of the given matrix. Also, we have mentioned that the Leverrier-Fedab method can be used to find all eigenvectors of a matrix, but the entire method takes a lot of times, that means the method is time consuming. So, several methods are also available to calculate the eigenvalues and eigenvector for a particular type of matrices. Now, in next modules, module 2 and 3, we describe several methods to find the eigenvalues and eigenvector for particular type of matrices.